can see, we need to solve for this truss that's sort of rotated sideways. You can see the pin and the roller will be facing sideways. And if you're asking yourself, well, when would a truss be turned sideways? Would that ever happen? Well, if you look, stadium, for example, you'll see trusses all pointing all kinds of directions. But of course, there are several here sideways coming out of the structure. And so this is a very realistic example. This is just a super simple version of one. Okay, so an extremely simple version. And as you'll see, solving for this sideways truss follows the same rules as before. So let's go ahead and start with step one, which is solve for the angles. And so I'll go ahead, obviously this is a 90-degree angle, we don't need to know that. But I'll call this angle right here theta 1, and this angle over here theta 2, because it doesn't really matter, as you'll see. But if we want to solve for theta 1, well, we need to know what sides we know. Well, I know the opposite side of this theta 1 is 3 feet. And then I can clearly see that the adjacent side, well, is 3 feet as well. This length is 3 feet. You just move this length down, it's still 3 feet. It doesn't matter that it's up there. And so opposite and adjacent, well, that's tangent. And since we're looking for an angle, that's inverse tangent, okay? And our opposite is 3, our adjacent is 3. And you might have already figured out what the angle is, because it's kind of obvious. But to figure it out, I'm going to go ahead and use my handy-dandy calculator. I'm going to use inverse tangent of 3 over 3. We hit enter, and we get 45 degrees. And of course, we get 45 degrees. Why wouldn't we? If you look, the sides are opposite. Therefore, the angles would be opposite. Therefore, theta 2 will also be inverse tangent of 3 over 3, which is also 45 degrees. Okay, so step 1 hasn't changed. What about step 2? Well, this is where it gets a little weird. The step doesn't change, but it does seem a little bit different because the roller and the pin are sideways. Well, our roller will still have one reactionary force, and it'll be perpendicular. So what does that mean? Well, since it's sideways, we're not going to have an upward reactionary force at joint A where our roller is. We're going to have a X reactionary force. And so we got reactionary force at joint A in the X direction. So good old racks, although it is implemented a little bit differently. It's no stranger to us, reactionary force at joint A in the X direction. But what is a stranger to us is, well, we've got a pin up here. You can look at this as a pin. Well, we've got at a pin, you have 2 reactionary forces. One that's perpendicular. So we got one here that we call that reactionary force at joint B in the X direction, which we can, I don't know, Rubik's Cube, I don't know. And then we've got a reactionary force at joint B in the Y direction, which we can call Ruby, and I moved that up, and you'll see why, hopefully very soon, why I wanted that up a little bit higher. But now we just need to solve for our reactionary forces, which is step 2. So normally I start with the sum of all forces in the X direction on these things, but because this is sideways, I'm going to go ahead and start with the sum of all forces in the Y direction. We know that's going to add up to 0, and there are only 2. There is 50 pounds going downward, and then we can add that to Ruby over here, or not Ruby, yeah, Ruby, the reactionary force at joint B in the Y direction. Those are the only 2 forces on this truss going up or down. And you can see that clearly the 50 pounds is going downward. Therefore, Ruby must be going upward, because that's the only way they can add up to equal 0. Therefore, we can set Ruby equal to 50 pounds. So we say Ruby equals 50 pounds, and we already solved for our first reactionary force. But of course, this means we got our direction of our force wrong, so we just go ahead and erase that or cross that out, however you want to do it, and we can redraw it going upwards as it should to cancel out the other force. And then we can move on to our other reactionary forces. The sum of all forces in the X direction also has to equal 0. And what are those? Well, we've only got 2 in this case. We've got racks, so reactionary force at joint A in the X direction. And we can add that to our reactionary force at joint B in the X direction. And I know that these 2 forces will cancel out. And since there's only 2, I know that they have to be equal to each other to cancel out. Although, if you notice, we don't really know which one is going to the left and which one is going to the right. We don't really have enough information. We can puzzle it out if we really look at it, but if we go on to the next step, you'll see that we'll actually figure it out pretty quickly. Or the next part of this step, this is still step 2, I guess, if I'm being technical. But I'm just going to know that these two forces have to be equal to cancel out to equal 0, and I'm going to puzzle out the direction of each one, continuing on with what I need to do next. Because I know to solve for either one, I have to use the sum of all moments. So we can go ahead and do that. We'll go ahead and write it out. We'll say, well, the sum of all moments will equal 0. Well, the next thing we need to ask ourselves is, what are the moments? Well, if you look, the first moment's going to be at joint C, because there is a force going down here. And we are going to continue going down and then towards our pin. Well, where's our pin? Our pin's over here. That is down and then up and to the left. If you look, well, what is moment C? Well, we could say it's equal to moment C plus something else. Well, we can see that moment C is clearly going clockwise, and that's a very important thing to notice, because therefore, whatever other moment we figure out, it has to be going counterclockwise. Well, if you look, we can't have a moment at the pin because there's no distance from the pin. There's a force. There's two forces here at the pin, but there's no distance at the pin. So the only place a moment can be to cancel out moment C is at our joint A. Therefore, we'll have a moment at joint A, and it has to be going, well, it has to be going counterclockwise. So if you look, well, which direction is counterclockwise, it would look something like this, and actually I can draw it a little bit better, but it would look something like this. It has to be going in some way in the circular form. So if we had it going to the left and then going towards our pin, that would be a clockwise moment. That would be incorrect. Therefore, we know our moment at joint A has to be going counterclockwise, and to make that happen, the force has to be going to the right. So if you think about it, moment C here, let me go ahead and delete this little tiny counterclockwise note that I made for myself, and then label this moment C. I'm sorry, not moment C. I don't know why I'm calling it moment C. I'm losing my mind in my old age, clearly. This is moment A. So as you can see, we puzzled out that moment A has to be going counterclockwise. Therefore, Rax has to be going to the right, and Rubik's must be going to the left. So we can go ahead and lose this as well. Hold on, let's go ahead and delete this part of our arrow, and we'll just cross it out, I guess. And redraw our Rubik's, or our reactionary force at joint B in the X direction, going the other direction to the left. And then we can continue on with solving for our moments. We can set moment C equal to moment A. And then we can just plug in our numbers and start solving for Rubik's and therefore Rax. Okay, so what is moment C? Well, it's a force and a distance multiplied together. We know the force is clearly 50 pounds. Okay, so we plug that in, 50 pounds multiplied by its distance. We only care about the perpendicular distance. Well, this is going downwards, so the perpendicular distance would be the left to right distance. Well, that's 3 feet. So 50 pounds times 3 feet equals, well, clearly it's going to be the force at joint A, which is Rax. So the reactionary force at joint A in the X direction multiplied by its distance. So what's its distance from our pin? Well, that's just 3 feet as well. And if you think about it, if this is 3 feet and this is 3 feet, then Rax has to be equal to this. This would be 150 foot-pounds. We can say this is 150 foot-pounds if we wanted to. We don't have to write it out. I mean, I can. It doesn't matter. 150 foot-pounds. But in order for this to be 150 foot-pounds, well, if you think about it, if we want this to be equal to RAX times 3 feet, we don't have to really do any math at all. We can just look at it for just a second and see that Rax clearly has to be equal to 50 pounds. You can go ahead and use the algebra, solve for Rax if you want to, divide by 3 feet on each side, but you'll clearly get 50 pounds. And if Rax is 50 pounds going to the right and Rubik's equals Rax, we can plug this in right here, and we can say that Rubik's equals 50 pounds as well. So as you can see, we just turned it sideways, but nothing really changed. We still follow the same first 2 steps for solving for our reactionary forces and solving for the truss.